Hello, this is Dr. H, and today I'm going to be talking to you about some action potentials in myocardial cells. A little bit more cardiophysiology coming your way. This particular video is going to require some background knowledge that I have presented in some of my previous videos. You should still be able to follow along without that background knowledge, but I do recommend going back and reviewing some of those videos for some of that information. But right now, what we're going to be looking at is myocardial. These are the muscle heart cells. These are the ones that are going to contract and relax. So these are the actual muscle cells that create the force that's going to put pressure on the chambers of the heart as they contract. And that's going to be what ejects the blood from the heart. So these are going to be doing the physical properties that drive cardiac output. In other words, these are going to drive stroke volume. I have described that in a bunch of my previous videos. The myocardial cells are found throughout 99% of the heart. They're have by far the largest numbers of all the cardiomyocytes, and they're found pretty much everywhere. So if we go to look at a heart, right, and we actually, let's just go ahead and draw an imposter heart here. The imposter heart is the one that most people know and love. And we're going to go ahead and divvy out those chambers. It's really easy to draw a heart out this way. It's not what a heart looks like. You guys know that by now. Right atrium, left atrium, right ventricle, left ventricle. It's a pretty simple way of doing this. And what you previously learned about is that there are autorhythmic cells and there are cardiomyocytes, and that the autorhythmic cells, well, there's only about 1% of the total heart is made up of autorhythmic cells. We have the SA node and the AV node, and the SA node is the natural pacemaker, and it creates a current, an action potential now that travels throughout the atria, then down through the AV node before going through the bundle of His, bundle branches, and out to the Purkinje fibers. Right, so we've seen this in some of the previous videos. Well, what those autorhythmic cells are doing is they're creating the electrical current that now goes shooting through the heart. And as that electrical current rushes through the heart, it's hitting myocardial cells. It's hitting myocardial cells here in the atria, causing atrial contraction. It'll be hitting myocardial cells down in the ventricles, causing ventricular contraction. So what we need to try to identify is how these myocardial cells are going to respond to that electrical current from the autorhythmic cell, and how that ends up creating contraction and relaxation. So let's go ahead and draw out our graph and try to understand what's happening at each step of this action potential graph. We've got our X and Y axis. The X axis is always time in milliseconds. The Y axis, I always try to write down sideways here, is membrane potential. And potential in science tells you voltage, and these are always measured in millivolts because things in the body are small. And we've talked about these sort of issues before, right? So what we're looking at with membrane potential is actually what's happening inside of the cell versus outside of the cell. So what is the relative charge inside of the cell versus outside of the cell? And I always go ahead and start by writing 0 on my y-axis, because if the charges inside of the cell and outside of the cell were the same, there would be no electrical gradient, therefore there'd be no membrane potential. And here in myocardial cells, what you're going to find out is that the resting membrane potential is way down here at negative 90 millivolts. What that tells us is that these cell membranes are packed full of potassium leak channels and don't have a lot of sodium leak channels. So the primary leak channel that determines the membrane potential in myocardial cells will be the potassium leak channel. And I have explained that in my previous videos as well. So let's go ahead and put in our dashed line. That indicates that this is homeostasis. This is resting membrane potential. This is where the body wants to be when it's happy and healthy. And what's going to end up happening is that the myocardial cell will be sitting down here at resting membrane potential, just minding its own business. And then what happens is that the electrical current derived from the autorhythmic cell that is shooting through the heart, as it hits the myocardial cells in the atrium and in the ventricles, that current is going to go flooding across that membrane. And as it does, it's going to cause this curve to just shoot straight up. This portion of the curve of a action potential for a myocardial cell is a representation of the current that's arriving at the myocardial cell from the autorhythmic cell. And that's going to shoot straight up, and it's going to end up passing threshold. And threshold you should always define in your head as the energy required to open up a voltage-gated channel. Always think of threshold as voltage-gated channels, and it's going to be no different here. When threshold is reached, we're going to have a voltage-gated channel that opens. And this is going to be a voltage-gated sodium channel. The same voltage-gated channel that y'all see with neurons, with skeletal muscle. With most of the cells of the human body, they're going to be driven by the voltage-gated sodium channel. We saw this was different in autorhythmic cell because the action potential there was driven by calcium. And that calcium flooding in is going to end up triggering these voltage-gated sodium channels everywhere else. So where's sodium higher? Outside the cell or inside of the cell? Well, the sodium-potassium pump is always pumping sodium out of the cell, driving the concentration gradient of sodium up outside of the cell. Therefore, sodium is going to try to go back through these channels, these voltage-gated channels. They're going to go from ECF to ICF. Long way of saying, what happens here as sodium goes flooding into the cell, it's bringing positive charges with it, and it's going to cause this to shoot up super rapidly all the way to approximately plus 30 millivolts. Okay, this is all due to sodium influx through a voltage-gated sodium channel. At the peak of the action potential for the myocardial cells, the voltage-gated sodium channel has to close. So that's going to be the next thing that happens, is that this voltage-gated sodium channel closes and something else opens. Repolarization in all the other action potentials that you looked at is driven by a voltage-gated potassium channel, and it's no different here. It's still going to be a voltage-gated potassium channel, but this is a voltage-gated potassium channel that opens and closes extremely rapidly. It opens and closes extremely rapidly. So it is a voltage-gated potassium channel. Therefore, potassium gets to leave the cell, causing the inside of the cell to be relatively more negative as those positive charges leave. However, there's something special about this particular voltage-gated potassium channel, and that is that it is extremely fast acting. It's called transient. Transient means only open for a short period of time. So this voltage-gated potassium channel is very transient. It's only open for this short period of time, at which point it's going to close. At the same time that the voltage-gated potassium channel, the transient one, starts to open, another one starts to open. But the second one that starts to open, even though it's starting to open here, it's actually starting to open at this point. It's a much slower voltage-gated potassium channel. The gate opens much slower, and it's not going to be fully open until way out here. But the entire time that it's starting to open, potassium is going to be rushing through it. Slow at first, fast at the end. This is going to be a voltage-gated potassium channel, but this one tends just to be called ordinary because it's the normal voltage-gated potassium channel that we learn about all over the place. So this one actually starts opening over here, but it doesn't become fully open until way over here on the right. So let's fill in the in-between. Let's fill in the in-between. Well, what's happening in between this point where the transient voltage-gated potassium channels close and this point where the ordinary voltage-gated potassium channels fully open? Well, here is when we're going to have these very specialized calcium channels open up. Right here, an L-type calcium channel is going to open. An L-type calcium channel, if you've seen my previous videos, I define it as a voltage-gated channel. This is a channel that will open up due to these voltage changes. And calcium has a higher concentration outside of the cell than inside. So when the L-type calcium channel opens, calcium starts entering the cell. That's bringing positive charges into the cell, which would make you think that it should start to depolarize again. However, since potassium is leaving at the same time that calcium is entering, what we end up with is this elongated plateau phase. Okay, it just kind of stretches out that action potential due to calcium influx. But eventually that L-type calcium channel is going to close, and when it does, the voltage-gated potassium channel, the ordinary one, takes completely over, and that's going to end up causing this thing to go shooting back down as it repolarizes until it reaches the resting membrane potential, and all of those channels are now closed. So that's the short and sweet of the action potential for myocardial cells. The first portion of this curve had to do with the current arriving from the autorhythmic cells through the conducting pathway, through that conduction pathway. And as it reaches the myocardial cells, whether they're atriomyocardial, ventricular myocardial cells, it doesn't matter. On those cells, there are voltage-gated sodium channels. So as threshold is reached, those voltage-gated sodium channels are going to open and they're going to continue to drive current into those myocardial cells. Eventually, those voltage-gated sodium channels are going to close, and these transient voltage-gated potassium channels open really fast, open and closed. Some potassium efflux, boom, they're closed again. And what takes over now is an L-type calcium channel. But at the same time, some potassium is still moving out of the cell through the voltage-gated potassium channel ordinary. So calcium influx at the same time as potassium efflux creates this big elongated plateau phase. That plateau phase ends when the L-type calcium channel closes and the ordinary voltage-gated potassium channel fully opens, driving the repolarization back to the resting membrane potential. I highly recommend that everybody writes out this flowchart. As you study it, don't just draw the graph. Don't just draw everything on this picture. You notice maybe that I haven't even added a few things like sodium influx here and potassium efflux there and calcium influx here and potassium efflux here. I don't write it into my graph because I want to learn it. If you spend too much time writing everything on one graph, you get overwhelmed by the amount of material that's getting thrown at you. That being said, there's a way, right? And that's just to list it out over on the side, what's happening at each step. So here we're going to have step 0. Here we'll have step 1. Here we'll have step 2. Up here, step 3. Here will be step 4. And here will be step 5. And then we're going to reach step 0 again down here. So at step 0, what do we have going on? Resting membrane potential. By the way, I'm a true believer redundancy is the key to learning. If you are one of my students, you already know this. So that's why I repeat these things over and over and over. Step 1. What did I say happens at step 1? Well, this is now going to be the action potential created by the autorhythmic cells reaches the cell membrane of the myocardial cells. So this is electricity arriving at that myocardial cell from the autorhythmic cell. So I'm just going to write AP from autorhythmic cell. AP from autorhythmic. Easy enough. You don't have to write everything down to learn. You can fill in the rest using that brain. At step 2, what's going to happen? Threshold is reached. So at threshold, what's going to happen? We're going to activate A with an arrow up, because we don't have to write everything out, a voltage-gated sodium channel. The other way to write this is a voltage-gated sodium channel opens. Doesn't matter which way you go about it. And due to the activation of the voltage-gated sodium channel, what ion gets to go what direction? Sodium is going to be driven into the cell. So we have net sodium influx. What happens at 3 up here? Well, the very first thing I hope you guys see is that those voltage-gated sodium channel, no, they got that inactivation gate that's going to close. It's got to close. If it stays open, sodium keeps rushing into the cell. Kind of. There's more to it than that, but that's a good enough thing to start to think about now. So you must talk about the closing of those sodium channels, because what if you took a drug? What if there was a poison from a snake that stopped the closing of those sodium channels? Now we got issues. Diseases that stop the closing of these voltage-gated sodium channels, or anything, any step of this. So that's why you should make sure that you understand that they must close. At which time the voltage-gated sodium channel closes, what's going to happen next is that we're going to be activating the voltage-gated potassium channels. That's happening next. These are the T-type. Okay, they're the transient type voltage-gated potassium channel. And when they open, what ion's going in what direction? We're going to get potassium efflux. What happens next at step 4? Don't forget, things have to close. So the voltage-gated potassium channels, the T-type, well, they're going to close. And what's going to open? The L-type. And when that L-type calcium channel opens, what gets to happen? Calcium influx. I don't need to write this in here, but at the same time that calcium influx is happening, potassium efflux is also happening through these ordinary voltage-gated potassium channels. They're just not fully open yet. So it's step 5. Hopefully I have enough room down here for y'all to see it. Kind of. Step 5, these L-type calcium channels close. Going to abbreviate for y'all so I don't run out of space. The L-type close, and the voltage-gated potassium channels, the ordinary, they're going to open. And what happens when they open? Potassium efflux. I am out of room for y'all. I'm going to write real small. And what's going to happen as that potassium efflux occurs? Well, now, right, we drive right back down until we reach resting membrane potential, at which time these ordinary voltage-gated potassium channels close again, and we're back at RMP. So that's the nuts and bolts of how an action potential in myocardial cells occurs. In the next video, what you guys are going to be learning about is excitation, contraction, coupling, and relaxation. So in essence, what the next video is going to be doing is it's going to be saying, all right, the myocardial cells get their action potential. How do they contract? And then the next step of that is we don't want just heart contracting. I don't know if you know, but that would be bad, right? If the heart just contracted and it didn't relax. So what we need to think about next is how does the heart relax? And it's all going to relate back to this information, and it's going to relate back to autorhythmic cells. Cardiophysiology is a comprehensive unit. Each piece leads to the next. All right. Hopefully that's helpful. This is Dr. H. See you in the next video.